No, you can join in the class. This the tomorrow afternoon is okay. Who cannot? I just want to say, any of you cannot. Okay, so maybe all of us can join in the classes tomorrow afternoon. That okay? So we have a class tomorrow afternoon. Of course, maybe one or two students can, maybe you cannot join in or no, but if it's just a few students, then please. Okay, so say fix tomorrow afternoon. Is that okay? We continue this class, and next week one more class in next week, and the next week we will continue our class, and we have some time for the two group who have not yet finished the presentation. Do presentation, okay? Okay, so we start our class. This is an example. The last time we have not yet studied it, but now we will do it. And the just a moment. The content for the final exam will be the content for the final exam. The last time we studied the this already, is that right? The we study for the chapter 2. We study transportation problem, and we just the first part. I think the first part is find out the initial BF solution or something like this. And the next time is streamline method. We have not yet do it, and we continue the chapter 2 and chapter 3. Is that okay? Just a moment. I check because I want to tell you exactly the content for the final exam. The content for the final exam, the midterm. Here, the midterm test. Just the BF solution. Yeah. So in the midterm test, the chapter 2, we just have the BF solution by the northwest corner method or something like this. And this is the streamline method for the For the transportation problem. The chapter 3 is a multi-objective linear programming, and the chapter 2 still have some part like district water district problem or something like this. Some content in the presentation. Okay, with the presentation of some groups like this. Okay, so we continue with the chapter 3, the multi-objective linear programming. Is here. The example you read. Example. That is a production planning problem, and that is normal. That is just a LP, just a linear programming, and nothing special. And you learned it in optimization 1 already, and now you can see it. A manufacturing company decides to maximize the total profit from producing 2 products, P1, P2, utilizing 3 different material, M1, M2, M3. So you know the company produced 2 kind of products, P1, P2, and each product we use 3 kind of material, M1, M2, M3. That's quite easy. The company knows that to produce 1 ton of P1 requires 2 tons of M1 and 3 tons of M2 and 4 tons of M3. Okay, take a look if I know. Let me write down the papers, and I should have another computer. Okay. Okay. P1, P2, M1, M2, M3. P1. So for 1 ton of P1, you see, to produce 1 ton of P1, so you require 2 tons of M1, 3 tons of M2, and 4 tons of M1. On the other hand, we produce 1 ton of P2, require 6 tons of M1. 1 ton of M2, 6 tons of M1, 2 tons of M2, and 1 ton of M3. Okay, it's like this. And the total, the total amount available material are limited to 26, 27, 16, and 18. 27 M1, the maximum of M1 is 27 ton, M2 is 16, and M3 is 18 for M1, M2, M3 respectively. So 27 M1, 16 M2, and 18 M3. Okay, so it is also known that the product P1 use profit 3 million yen per ton. So P1 use 3 million yen per ton, and P2 use 8 million per ton. Okay, given this limit material, the company is trying to figure out how many units of P1 and P2 should be produced to maximize the total profit. Is that okay? This production planning problem can be formulated as a linear programming. Very easy. I go to the rough paper and tell you, just remind you one of the model of linear programming that I think that Professor Hai already teach you in the optimization one. So take a look like this. A company want to produce two kinds of products, P1 and P2, and each to produce this they use just this moment, they use three kinds of material, M1, M2, and M3. Is that okay? And 1 ton, in order to produce 1 ton of P1, we need 2 ton of M1, 3 ton of M2, and 4 ton of M3, like this. And in order to produce 1 ton of P2, they need 6 ton of M1, 2 ton of M2, and 1 ton of M3. Is that okay? The material, the total material, the total M1 available is 27 ton. M2 is 16. The total, the maximum of M1, M2, M3 is it, and 18 ton. Is that okay? Another thing is that you produce 1 ton of P1, you can sell it to get the profit is 3 million yen per ton, and P2 is 8 million yen per ton. Yen here, the I don't know, yen is Japanese yen maybe, or because the currency of Chinese is also something. I don't. They also write that yen or something like this. So, but let's say Japanese yen. 1 ton of P1. When produce 1 ton of P1, they get 3 million yen per ton, and P2 is this. And the question is, how many units of P1 and unit of P2? Here. How many ton of P1? How many ton of P2? The company should produce to get the maximum profit. Okay, here is profit. Okay. So this problem can easily to be seen as linear programming. You know it very easy. So if you let X is the amount of P1, number of ton, the unit is ton of P1, and Y is the number of ton of P2, the company will produce. And then 1 ton of P1, you need 2 ton of M1. So X ton, you need 2X ton of M1, 3X ton of M2, and 4X ton of M3. Is that okay? And for the P2, for the product 2, Y, so 1 ton, they need 6 ton of M1. So 6Y, 2Y, and 1Y. Is that okay? So you see here, and you see the first that the maximum available of the of the M1 can be used the maximum, not more than this one. So the total amount of M1 is this one, must be less than or equal 27. The total, if you produce xp1, yp2, and then the total, that is the total M1. The total amount of M1 can be used is this, and this cannot be greater than 27. That means must be less than the amount of material available. Is that okay? And the total material M2 user cannot be greater than this one. This is the same like this. So you have the three inequality. Okay, and then the profit. If you produce xp1, 1p1, you get 3 million yen of 1 unit. If you produce x unit, then you have x. You produce a y unit, then have y, and the total profit is this. The total profit is this, and this should be the maximum. That okay? And then you can get the problem, linear programming. The minimum of this, so that you have the inequality, three inequality here, but there's some extra thing is that the number of x is greater than 0, and the number of y is also greater than 0. And that is linear programming. Okay? The linear programming here. So you see this model, just the maximum of this and this one. And so this model is the model of linear programming like this. Is it okay? This model programming you can write down like, yeah, that is the, I write down there is the max. Max of 3x, just write down x1, x2, I write down x and y, and now it's y, so it's okay. 3x1 plus 8x2. Is that okay? So that you have the inequality like this, and one is like this. But now we want to change to the problem of minimum. We change minimum by changing maximum into minimum of minus 3x1 minus 8x2. Is that okay? Problem of maximum profit become the minimum of this. Okay, and then it's the problem like this. So we have this problem. I just remind you in linear programming, you can write out it in the form like this. It is mean. It is mean of minimize of minus 3 minus no. Minus 3 minus 8, and then like this, x1, x2. If you write down in the matrix form, okay, and you have something like this: 2, 6, 3, 2, 4, 1. So x1, x2 less than or equal 27, 16, 18, and then you have x1, x2 here is greater than 0, 0. So the problem in this form we call the linear programming. Okay, it's clearly that's linear programming, and it is in matrix form. And then okay, matrix form. Yeah, that's okay. This is just a model of the linear programming, but we are in the chapter of multi-objective linear programming. So that means and you remember here is a objective objective function. Objective function is here, and it's also here. Is that okay? This is an objective, and this problem have only one objective. One objective means that it's normal linear programming. Is that okay? And now we have we try to introduce something situation where the objective have not only one but two. You read the sentence I write down here. In the case where people concern some more goal, which also must be minimized or maximized, such as to minimize the pollution pour out to the environment in the production process. Suppose that this kind of process are producing the two products P1, P2 in P1, P2, it produce some kind of pollution, and the pollution is proportion to the amount of product. For example, you produce more and more product, then the pollution is introduced more and more. Is that okay? And so in the case you here you just produce to get profit. Maybe you may produce more profit, P1 and P2, and get more profit. But in that case, the pollution will increase. Also produce also more and more. And so you have two things here, two objects. One object is the profit maximum. You want to produce the amount of X1, X2 so that the profit is maximum. But on the other hand, you also want to produce the number amount X1, X2 so that the pollution will be minimized. Otherwise, you have to get the penalty or something like this. Okay, so look at. We continue this example by doing something like this. The continuation of the example. Unfortunately, however, in the production process, it is points out that the product P1 yield 3 units of pollution per ton. You produce 1 ton of P1, then it produces 5 units of pollution. And product P2 yields 4 units of pollution per ton. So you produce X ton of P1, X1 ton of P1, X2 ton of P2, and then the total of pollution will be like this. Total pollution. Amount of pollution is this, and this should be minimized. Is that okay? And now you bring it to the problem here. So you have two objective function. One objective is minimize Z1 and minimize Z2 equal 5x1. 5x1 plus 4x2. Okay, so minimize two things. So the problem is find out x1, x2 so that it minimizes at the same time two objective function. Okay, and if we write down the problem and then the problem like this, but the first one here is you have Z2, so it is 5, 4, like this. So if we write down in the matrix form, we write down minimize. Okay. Minimize this 5 4 here, minus 3 minus 8 5 4 x1 x2, two things. Then it is like this, 2 row here, and then subject to like this. The condition is this the same. The condition is the same. It's just the adjective function. You have one more here. Okay. This problem is called multi-adjective linear programming, and multi-adjective in this case just only two adjectives. So you in normal okay, in real problem, practice problem, maybe three objective, 4 objective, something like this. Is that okay? You can yeah, this is just the multi-objective linear programming. And you remember that your final exam have two parts. The first part is presentation. You mean that making putting the presentation to the final exam just make me busy, a lot of a terrible thing for me. It would create some more thing for me to do, but it's help you. The presentation often you get mark, it's good mark. So 30 mark for the presentation, and you have 70 marks for the writing. Writing is the same like the midterm test, like that. But the presentation 30 marks, and presentation is in group, and we make in 3 groups. It's the same like the group we make presentation in class normally. And one of the topics of the final exam is create or find out. You can find from the internet. You can find the internet, and then you can find it in some books. You can have it in the internet, and then you can modify to be to have a nice one or something like this. But one of the topic is find out a model of the real multi-objective linear programming. Just two objective is okay. And with this, so you see you have the problem here. The two minimize of two things, two objective, and the constraint is the same. This problem, in general, you may have here k. You may have k objective function, and this is the k objective linear programming, the linear. Subject to this one, this one you can write down like this: 2 6 3 2 4 1. Here is x1 x2 less than 27 16 18, like this, and then x1 x2 is greater than 0 0. And here you have the form. Here is the form like ax less than b, x greater than 0. We write down like this. Is that okay? And that is the matrix form. And this one you can write down as minus 3 minus 8, and then here 5 4, and here is x1 x2, and we also like something like a c, and then x1 x2. Is that okay? Or cx. Or you can say here is min of Cx. Cx to min of Cx subject to this. So it's minimize Cx subject to, and this is a multi-additive linear programming. That is multi-additive linear programming. We call LLP like this. So that is a matrix form, and of this example, and in the if you have the here A like this, B like this, so that is AX less than B like this, and X is greater than or equal 0. And if you have C here, and then you have the additive is minimize here CI, C1X, C2X, something like this. So it is CX. Okay. CX, and C is equal to C1X. So you have something like this. C1, C2, CK, and X. C1 is it. C1 is equal something like C11, C12, C1K, and here X is X1, XK. See? So let's have this form. They can write down many ways. Like you can have here is AX less than B and X greater than 0. That's I think J. But they minimize. They can see that minimize ZX. They write down like this. It's equal to Z1X, ZKX here. And so maybe Z1X like this, Z1X equal to something like this, C11, C12, C13, C1N. And then here is X1, XN. Z1X can be like this. ZI, for example, you have here ZIX, and then is CI, 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 like this. Okay. But anyway, many way to write down. But the most common way to write down is that is the matrix form. C like this. C is matrix. C can be written down like this. That means that is equal to C1, CK. And each of the CI here, each of CI is a row vector. CI is row vector. So you have, that is a key point. You understand? The model of linear programming, multi-additive linear programming. So you have several. This is the additive, minimize some additive, but the additive they have several function. Okay, several additive function. Okay, and in our example 1 and 2 there, and the model is this. You understand? Hello? Somebody? Bùi Tố Ma, you understand?
Yes, I can understand, sir.
Okay, thank you. Let me check the attendance list. Today is June 3. June the 3rd. Yeah, it's okay. Okay, and we continue. In order to understand the linear normal linear programming, that means one objective, and you raise up to two objectives. The problems are very different, and it become very difficult. Why? It is like this. You suppose that you have this in R2, you have a tree inequality and like this, and so the set, we call it the set F. F is a feasible set. The feasible set. Is that okay? Suppose that you have only one. You have only one objective. It's just like this. And so it's linear programming. Is that okay? And you see that here. This is a feasible set of our example. The feasible set is it from this point is E, this point is O, this point is B, this point is C, this point is D. So the feasible set is this. Is that okay? The feasible set F is this. Is that okay? And then what is the objective function? The objective function is that x equal minus 3 minus 8 minus 3x1 minus 8x2. Is that okay? So what is it? Minimi of this. Minimi of this means what? Can you imagine you have something, the problem of minimi of this, and ax less than b and x is greater than 0. The x satisfy this is the set of all x satisfy this, we call the feasible set, and it is F. Is that okay? And F is here. So what does it mean, this problem? What does this problem mean? This problem means that for any x, you consider each x of this, each x1, x2 belong to F. Each x1, x2 belong to F. You have this value. Say, each this, you have this. We have each of this, we have the value zx equal minus 3x1 minus 8x2. Is that okay? You have one value. What is this value? This value is belong to R. I think that this you learn from Professor Hai already. Is that okay? So what does it mean? What is it? It means that for each like this, you have the value like this. So that means that you have a map, a function. you have a function you call, this is the function z. The function z from f to r. Is that okay? Each x1, x2 give you zx belong to r. Is that okay? Each x1, x2, you get this in r. And so in r, suppose that this is r. Suppose that this is the set of r. Is that okay? So each x here is x1, x2 here. You have something here. Z of x1, x2. You have, or you have each x1, x2 here. You have z of x1, x2 is here. Is that okay? And then for all x in this, x is running all the f, and then zx running in somewhere here. Here, and this is the set. This is the set z of f. Is that okay? You understand? You have a map z from the set f to r, and you take each point. You take each point x1, x2 here. No, let me write down is in very. Each point x1, x2 here give you a point z of x1, x2 there. Is that okay? In R. So if you take x1, x2 running in all of this set, all of the set, x1, x2 running like this, because the function is linear. The function is linear, and so the image of all this is this set from here to here. Is that okay? And what is the solution of the problem? What is the problem? The problem means that for any x, the problem here, for any x in f here, what is the, for any x1, x2 in f, in this set, in f, what is the value x1, x2 such that this attain the minimum? You see? Which attain the minimum. And so that means that if you make the set ZF, what is x1, x2 so that Z of x1, x2 attain the minimum of ZF. What is the minimum of ZF? The minimum of ZF is here. You see what I'm writing here? The minimum of ZF is the red bond there. Hello? You understand? The minimum of ZF is there. And this is the minimum of, this is the value of this problem, alpha. The value of the problem is alpha, minimum is here. You see? Hello? Do you understand? Lê Nguyễn Đăng Khoa, you understand Khoa? Hello? Đăng Khoa, you are there or you sleeping?
Yes, sir.
You understand?
I'm here.
You understand what I'm saying or not? Đăng Khoa, hello.
Yes, sir.
Let me repeat it. It seems that you. Hey, we look at the problem again. Okay, the problem is here. For the linear programming, you understand? I just want to say about the linear programming here. Okay, and the feasible set here. The feasible set here is F here. The feasible set here is F, and F is here. That okay? The feasible set is the green one. That okay? The feasible set is the green one. And what is the problem? The problem normal linear programming with one objective function means that each for find the point in the set F, find the point satisfy this. That means the point in F, so that the function zx here attain the minimum. Is that okay? Attain the minimum. So what is the minimum? The minimum here means each x in F, x1, x2 in F here, you have Cx, Zx is one point here. You take an x here, you have Zx is some point here. Is that okay? In this. Suppose that, so if we take x, we give, let x move all on the z1, z2, like this, and then the value of zx, z of x1, x2 is here. The value of z1 and z2, z of x1, x2 is on this interval, alpha beta here in R. Is that okay? And so the problem become very, very easy. Find out x belong to F so that the zx attain the minimum. But what is the minimum here? In the interval alpha beta, minimum is alpha. Is that right? Minimum is alpha. And you know the minimum is alpha is the value of the problem. In of the problem. Is that okay? First of all, you find out the infimum very easy because the value now is just the interval. Actually, there is some mystery here. Let me tell you. Let me ask you. Actually, let me ask you. Here, so you have the problem that is F, and you have the Z is F to R, and the set F is here. Is the polynomial. Is that okay? Polynomial. Of this. And what is Z of F? So the set of all this, I claim that this is R. Z of F is a closed interval. For example, AB like this. Z here. For example, you have a point x1, x2. Let me write you. You have the point x1, x2 here. And then it becomes something like Z of x1, x2 is some point here. Is that okay? And I claim that when x is moving inside the polynomial F here, F is moving in all like this, then the set of ZF is this an interval AB, just an interval. And the question is why? Who knows? Why? For example, Z app can be like this or not. Z app can be AB here, and then CD is two things. Two can be two interval like this or not, or just one. It can be two interval like this, A, B, C, D. ZF, I know, I tell you that the set Z of F can be like this or not. Two separate interval like this or not. Somebody knows? These are from the linear algebra. This we have to come back to linear optimization. You study already linear algebra. This is actually about linear optimization, but the base is the linear algebra. You study 4 periods for 4 credits linear algebra and 4 credits for the optimization one, including linear programming. So tell me, Z of F, that means the image of the F by the map by the function Z can be two separate closed interval like this or not? I say no, but why not? Any of you understand? Nobody knows. Hello. Lê Phạm Hòa Thương. You know?
I don't know.
Anh Thư.
Yes, sir.
You know, is it possible that that app is will be the unions of the two interval like this or not?
I think it's in the interval C and D.
So now I ask you, it can be two interval like this or just only one interval?
I think just only one.
Why? I claim that it is one. Here, AB, just only one. But I suppose that it can be two or not. Any in the class? You oh my God, you learned this in I think in the let I check the midterm test, some marks of the midterm test. Oh my God, scan it. Oh, no, I don't know. I could. It is in the. It's okay. Somebody knows. It's funny. Nguyễn Minh Quân.
Yes, I'm here, sir.
You know that CZ and Z of F can be one interval like this, AB like AB, or can it be two interval separate like ABCD here in the right of my figure?
Uh, I think that here on the figure, the feasible region S is somehow the closed and connected region, and the objective function Z is a continuous function. So the image of the feasible region over a continuous function here should also be closed and connected. So it should be one interval only.
Why? Why is it one and connected? Which I don't know how much you study in the metric space, but just a linear thing. They, do you know how you know about you learn one course about linear algebra already, and you also learn about convex function or something like this in optimization one. So I mean, want to ask somebody else if somebody knows about this. Oh my God. I don't know why in this meeting just only 9 students. Why? But today many students are absent. Somebody leave the class. I just see, for example, Quang Khai is already here, but he leave the class already. Maybe it's funny.
Dạ thầy ơi, mấy bạn rớt mạng đó thầy. Mạng đang yếu.
The set app is a convex function. Is that right? Is a convex set. Is that right? It is convex set. And so by the map, by the function z, the function z is linear. The linear map, the linear functions transfer a convex set to a convex set. Is that okay? You know this? Hey, prove you if you don't know it, you can prove it easily. You have the linear function. The linear function z, for example, from f to r. Then f is convex, then z of f is convex. And it cannot be like this. This set is not convex. Is that okay? Two separate like this is not convex. And so cannot be like this. It should be like this. It should be like in the right hand here. But why it is closed? Why it is not like this? AB. Why it's not? It's like this. The function up here is linear. So how you say? So app is is closed, then you will have that is closed. It's compact. F here is compact. Is that okay? And C is continuous. And then CF is compact. Compact in R, and it should be closed. Is that okay? It should be convex and closed. Convex and closed is closed interval. And what is the problem? You have the linear programming here, then here, and then what is the meaning of the problem? I spend more time to explain to you so that you can move to the to the multi-applicative linear programming. As you will see, it things will be difficult. So that means that the linear programming is meaning of this. So if the problem is find down an x in the set f such that zx attain the minimum, and here you know the minimum is alpha here, the red point here, and you just find out the x1 x2 so that it's z of x1 x2 become the minimum. Is that okay? That's all. And how about the multi-objective linear programming? Multi-objective linear programming is a bit here, like this, difficult. You have here the set Z. The set here is F. Is that okay? You have F is E, O. I don't know. I don't remember exactly, but it is something like this. This. Let me check. Okay. E, O, B, C, D. It's like this. Here. O, E, B, so here. No. C, here, D. Terrible. I don't know what happened. This sometimes it's happened. B, O, E. Yeah, like this. C, D. This is the set F. Is that okay? The set F is here. And now each F, each x1, x2 here. For example, you take a point x1, x2 in Z. x1, x2 here. This point. You set that point this. And then the map Z. What is the map Z here? The map Z now is become what? From F, but 2. The map Z, but here is you call this matrix is C. Is that okay? And that ZX equals CX. That X equals CX and C is matrix. And so let's be to what? What is ZX? ZX is a vector in R2. Is that okay? And so it is in R2, not in R anymore. It is in R2. Is that okay? This is in R2. So if you have a point, if you have the points z x1, x2 here, and here you have z up x1, x2, this is belong to R2. And so what is that f? You have another here. For example, this is in R2. Z1, x1, x2 here. So it become here, the some point here, z of x1, x2. Is that okay? Like this. And here you have f, then the set of all. So let us say, what does it mean, this problem? The problem means what? Hello, Tammy. You are there? Do not turn on the mic because it is
Yes, sir.
there's some noise in your place.
Okay, okay.
Here you look at this problem. What does it mean, problem? That you find the bond among the bonds satisfy this. That means among the bond of F, find some bond such that the function z attain the minimum. Is that okay? Attain the minimum, but the minimum is minimum in R2. So you set that I have the set F here, and maybe so it's the same like before. You find out z of F. What is the set of z of F? Maybe something like this. It can be it can be like this. Just a moment. ZF can be like this. Yeah. This is our x, our y. Like this x1, and here is the x2, and the ZF is here. No, ZF is I write down it is in red one. ZF is here, the red one. Is that okay? With the linear programming, ZF is just an interval. So you can find the you know what is the minimum. The minimum is from AB, then minimum is A. It's quite easy to find out the minimum. And now the set ZF is here. What is the minimum? You know, where is the minimum of this set in R2? So in order to understand clearly the multi-objective linear programming, you need to understand what is the minimum means what. Minimum means smallest one, and small means what? The 2 points are small. 1 point is smaller than another one. Which sense? Here. Suppose that you have in R2 here x1. You have 1 point upon A and upon B. Upon A here and upon B here. How can you compare these 2 points? Which one is smaller than another one? Or which one is bigger than another one? In R, you see, in R you have something is A and B. Okay, A is less than B. And if you have C here, then B is less than C. It's quite easy. But in R2 here you have the 2 point AB. So how can we define a relation greater than or less than or equal in R2. That problem. So you cannot know which bond is bigger than another bond. You have not yet defined that one. And then in this set, you cannot find out which one is the minimum. You understand? Minimum is smallest one. But smallest means that if you compare with the other, it is smallest. But how to compare one bond to another bond? Like we have the 2 bond AB here. How you compare A and B? Which one is smaller than? You know? If you compare the Y, and then Y of B is here, less than Y of A. Is that okay? But if you compare, if you count the X, then you see XA is here, and XB is here. XA is less than XB. That is funny. That okay? So in order to understand the meaning of the way how to deal with the multi-aptitude linear programming, we have to understand the order in Rn. The 2 bond in Rn, how can you know that this bond is greater than or smaller than the other one? Okay, that is the first thing. And because, and it's I will tell you that the order in Rn is quite complicated, and so it gives you in R just only one. You have a one AB here, then the minimum is only one. But for the set in R2, because the complicated of the order, it has several minimum bonds, and similar way of consider the solution. You understand the solution in this way, somebody else understand the solution minimum in another way, another meaning, another way of understanding the meaning of the minimum. And so for the multi-aptitude linear programming, we have several solution notion of solution. Pareto solution, weak Pareto solution, strong solution, and absolute solution, or something like this. Many notion of solution, and each of solution like this. For example, weak Pareto solution, there's a lot, not only one like in R. Is that okay? So there are a lot. And so that's just the first thing in order to study this problem is not quite complicated, because linear is the easiest one. But because it's a multi-aptitude, the value is in R2, R3, R4, and so we have to study, first of all, the key point is the notion of solution. Is that okay? And now we should have a break. We have a break. I think 15 minutes. It's okay. So now it's 35, 40, 35, 15. Okay. Then we come back. I see that until now there's the number of students become for 13. That's still some student not that in the class. Okay, we stop for a while. Stop recording.
Yes, I see it, sir.
Okay, thank you. So we come back to the I just tell you the general meaning of the problem multi-objective linear programming. It is you have a set we call feasible set, and we have the map from the feasible set to the space of Rn, at least R2, R3, R4, something like this. And we have this map, this linear map C. Linear map C will transfer the feasible set F to CF. Well, okay, this is C. The C is here. Here, C is a matrix. And you know, in linear programming, in linear algebra, you see, you have a matrix C. The matrix C is also matrix C. Let me tell you you have a matrix C is Cij is m by n. So that means m row and n column. Is that okay? N column. And then this C can be considered as a linear mapping from Rn to Rn. Is that okay? And x in Rn here is equal to x1 to xn. It become Cx. That means the matrix C multiplied by x. Is that okay? That is something like a Cij and then x1, xn. And this vector is in Rn. Is that okay? So from now on, we will use this notation. C is a matrix, and also a matrix is also at the same time is a mapping, linear mapping, or we call linear operator. Linear operator. Is that okay? That's one thing. Now, for the because we are preparing for working in Rn. So in Rn we need, you know that CF is in Rn, and Rn, and now we need to compare the two elements, which one is bigger than another one or something, so that we can have a minimum. Okay, and so we need to consider the ordering in Rn. And one of the, in order to set up Rn with an order, then we can use a cone. Normally it's convex cone. But in our in the content of the multi-objective linear programming, the cone we use is Rn plus. Rn plus, you know what it is? It's the first octave. It is Rn plus means Rn plus equal to R plus multiplied by R plus multiplied by R plus. Like this. Is that okay? And the time. And we here. And the convex cone Rn plus will generate an order in Rn by setting like this: x less than y. If and only if you have x equal to x1, xn, and you have y equal y1, yn. Is that okay? You have this. And then you have x less than y definition defined by xi less than yi. I is 1 to n. So that means that the first point x, the point x is less than the point y if and only if each corresponding coordinate of x always less than y. the corresponding coordinate of y. That looks easy, but if you just use this, you cannot work with practice problem. A remaining equation is minimize a vector function. We minimize cx. Is that okay? Actually zx, and now we write out cx. We minimize cx. It means that minimize the vector function c. Is that okay? And cx is a vector in Rn. Okay, and how should we understand the minimize? How should we understand minimize? In what sense? Is that okay? And then we, in other words, minimize means what? And it means what is the solution of the multi-additive linear programming? Minimize in what sense? That is an idea. And now, in order, I need you to understand a little bit more on this. Is that okay? So that you can check the 2 points, which one is less than another one or something like this. So we come to the rough paper and I tell you. Now we have x. A vector x is x1, xn. And vector y is equal to y1, yn. Is that okay? And we say x less than y. So by definition, if and only if x1 less than y1, x2 less than y2, oh, no, and then xn less than yn. But what does it mean? What does it mean? This means that it's equivalent to what does it mean? It means that y1 minus x1 greater than 0, y2 x2 greater than 0, yn minus xn greater than 0, like this. And this is the same like there, but it means that the y minus x, the vector y minus x belong to Rn plus. Is that okay? This is can be write down like this: y minus x equal y1 minus x1, yn minus xn, like this, greater than or equal 0, 0, 0, 0, 0, like this, and that means that like this. But if you can write down like this, then you can write down like this: y belong to x plus Rn plus, and that is the key point. You remember that is x less than y, Rn. We write down x less than y, and by the cone Rn plus. This if and only if you have this one, and or after all if and only if, like this, Rn plus. X less than y is. So what does it mean? It means that here, for example, in R2, R2 is you have x1, x2, or xy, or something like this. So you have what is R1? This is R2. This is R2. So what is R2 plus? R2 plus is here. The red cone here. The red cone here is R2 plus. See? And now you have x less than y, x less than y. By this code means that y belongs to x. For example, here, this is x, and that is y. If x plus Rn plus, you know, do you know what is this set? Who knows? Who tell me what is this set? X plus Rn plus is what set? Hello? Nguyễn Vinh. Vinh there? You are there? Hello?
Yes, I'm here. Yes, I'm here.
Do you know what is the set? Can you show me where is the set X plus Rn plus? You know? Nguyễn Tuấn
It's
Anh.
RN.
Yeah. Okay, Vinh, continue.
Think it's RN.
Rn. In this case, in our case is Rn equal 2. So in this case, R2 plus. X plus R2 plus is what? Somebody knows? It's funny. You are.
I think that the x plus R2 plus is the translation of the first quadrant by the vector x. We translate the first quadrant by the vector x.
Yeah, that's right. Thank you. You are Nguyễn Minh Quân, is that right?
Yes, sir.
Quân, you get 5 points bonus. Today is June 3. In R2, x is like this, but it also can, upon x can be considered as x, but it's also considered as a vector. Like this. Is that okay? And x plus R2 plus means that the R2 plus is translated by vector x. So it means that it is here. Let me do it here. The R2 plus is the first octant here. First octant you move by the vector x, and then it becomes like this. Yeah. The black one here. It is x plus R2 plus. The black one. Yeah. That okay? And you see in this case, y is here. Y is here. It is in. Look. Look at this. Y is in x here. X plus Rn plus. And then y is bigger than x. Is that okay? In this case, we say y is bigger than x. And if you check, you can draw from the point x. You can here translation of the first octant to this. Then if y is inside, then y is greater than x. If y is not inside, then it's not greater than x. So suppose that you have here, you have upon, for example, you have this point is y1. Y1 is this point. And so y1 is when you move, you take x plus R2 plus here, but y1 is outside. It's not in. So you say x is R2 plus not, x is not greater than, not less than. Is that okay? That means y1 is not greater than. So you see, in this case, y1, you say the x coordinate of y1 is bigger than x, but the y coordinate is less than. So all the x coordinates and y coordinate bigger, then it is bigger. Otherwise, not. That okay? So, but how about how you compare x and y1? X and y1, you have x is not less than. But do you see y1 is less than x? Y1 is less than or equal R2 plus of x. If you want to say like this, you have to move R2 plus to y1. Is that okay? And then you see, if you translate y1 is here. You translate the first octant to this, and then you will have something like this. The yellow one. The yellow one is y1 plus R2 plus. And so you see x is inside or not? No, x is not inside. X is not inside. So x cannot be greater than this. So you have this. So what it means what? It means that in R2 with the order generated by R2 plus, it can be, there are some points, for example, x and y1, x not less than y1, y1 not less than x. So that means the 2 point x and y1 cannot be compared. Cannot be compared. So you think up, find out the minimum of a set. Minimum of a set in the normal sense that the minimum of a set should be less than all the points in the set. Is that okay? But here you see in R2 is maybe not the case, because maybe there are some points which is this not less than the others. Is that okay? So how can you compare? For example, you have this is R2, and suppose that you have the set. Suppose that you have the set here. Suppose that CF is here. Suppose that, so you have this point. You consider this point is x, and this point is y. The same as before. If I remove this one and write out like this, then y is not inside. So that is x not less than y. Is that okay? And you move y, you do something like this with y. This is y plus R2 plus. Then x is not inside. X is not inside. So y is not less than x. You see? So the set CF like this. Some point in the CF you cannot compare them together. And so how do you find out the minimum? Minimum should be less than all the others. Is that okay? In our mind is this. Minimum in R, we consider in R. So upon its minimum is less than all. All the other must be greater than. This is the minimum. Is that okay? But here in the set like this, you have some point you cannot compare together. So how can we understand minimum? That's big trouble. Is that okay? You cannot understand the minimum. You cannot understand the problem of multi-adaptive function, multi-adaptive linear programming. And you cannot understand, you don't have the notion of solution. What is the solution? So how can we solve it? and we cannot solve it, that means that some real problem like the problem we tell you there, maximum the profit, minimum the pollution, cannot be solved. Okay, so people try to think up some kind of solution. Okay, and the kind of solution here is we study here. We have several kind of solution, and the first kind of solution is complete optimal solution. The setup the upon satisfy the constraint of the problem. That is the feasible set. I write down here already the feasible set. This feasible set is denoted by X. Is that okay? Like in the example there, I write out F, but now in this lecture notes we write out is X. That's still okay. Now, upon X star in X, that is a feasible point. A feasible point is said to be complete optimal solution of the problem of the multi-objective linear programming if here means if and only if. You see, if in definition is if and only if. Zi of X star is less than Zix for all I want to K. You remember? Let me tell you here, because we write down like this. I will write down like this. Cx. I write down Cx for the short way. We write out Cx. Cx means something like this. Z1x, Z2x. That is Zx there before. That okay? We write out before we write out Zx, but now I write out Cx. But Zx is equal to C, the matrix C multiplied by X, like this. So instead of writing Zx, now I write out Cx. But in this lecture note, the notion is still use the notion in the book, and so this is equal to Z1x, Z2x, Z3x, and here it's, oh my God, terrible. I write down here Zx. I don't know I don't write out this anymore. I write out Cx. C is what? C is a matrix Cij, and it is K by N. So it is Cx is equal to something like this. You write down Z1x, Z2x, and ZKX. Write out this way. Are okay? Like this. And we also sometimes we also write down like this. C1x, C2x, CKX. Ci here is the row of C. The row of matrix C, you know, the row of matrix C multiplied by X. So C1x, C2x. You understand? You have to understand really clearly this, so that later I can make things more simple and easier for you to understand. Like this. C. The matrix C is it. C equal C11, C12, C1n, C21, C22, C2n, CK1, CK2, CKn. Like this. Is that okay? And then the C1, I write down like this. It's equal to C1, CK. So C1 here is this. It means that C1 here is the first row. You know, the first row. This, and so if you multiply by cx, and then here is x1, xn. Is that okay? And then it's equal to c1x, c1x, c2x, ckx, like this here. That's the notation we will use. Is that okay? Now, here, complete optimal solution. Complete optimal solution of the multi-objective linear programming. X star here is called the complete optimal solution. Means that Zi mean that Ci. X star. Then Zi, that means Ci of X. Is that okay? For all I. That means you have Cx star is less than, but Rn, here the order in Rk plus Cx. So that means you have this. For any X, for all X in the feasible set. That means that for all X in the feasible set, C of X star is the smallest one. This is the so-called complete, complete. Here we can, a complete X star is a complete optimal solution of the multi-objective linear programming. Means that Cx star is a strong minimum point of Cx. Let me, we have another definition here. Complete optimal solution. Strong minimum element of a set. Oh my God. You hear the they terrible. Does it the singer there disturb you? You can hear me? Hello?
I can hear you, but the singer is very loud, sir. Very loud.
Okay, so it's okay. The neighbors, I don't know, sometimes they, so it is like this. So this means that Cx star is less than Cx for all X. Is that okay? So it let come back to the example here. Suppose that you have here. Suppose that we have something like this. Vietnamese terrible. Suppose that the Cx is here. Suppose that here is C of X star, C of X star is here, and this is a C of X. So that means that you have the set X somewhere here. You have the set X somewhere here. Is that okay? set X. Is that okay? And by the mapping C, by the mapping C, this is Rn and this is Rk. Is that okay? X, and then by the linear mapping C, it becomes like this. And this point is Cx, Cx star. There is a point X star somewhere. For example, X star is here. X star is somewhere here. Cx star is here. And you take an X, you take any X here, and then you will see Cx is somewhere here. Is that okay? And for any X here, Cx is always here. For any X is in like one here, the Cx is always, the set of Cx is here. And then you see, if you draw the Rk plus here, and then this set is C of X star plus Rk plus. Is that okay? This set is this. And you see all Cx with X is in X. X is in X here. All Cx is here. And because it's here, it is Cx for it's always belong to this. For any X belong to X. Is that okay? And so that means that Cx, in this case, we have Cx star less than or equal Cx. Is that okay? For any X in X. And in this case, we see X star here is a complete solution of the LMP, the linear multi-objective of MLP, multi-objective linear programming. You see, in this case, we say Cx, X star, Cx is smallest one. Is that okay? Among all the other, Cx star is smallest one among all the Cx, and so X star here is a complete solution. Complete solution. Is that okay? But this is quite nice. If you come back to the linear programming, you see that is the smallest one. The minimum is smallest one. That is okay. But normally Cx is not always nice like this. For example, the set of Cx is something like this. C of x is this. And in this case, no complete optimal solution, because there is no one which is smallest one among this. Is that okay? And many cases it is this. Rarely the problem have a complete solution, and so complete solution, if you define something, but most of the problem have no solution, then it's meaningless. Is that okay? It's meaningless, and so we try to think up another one. But by the way, if you have a set, we learn another terrible. If we have a set like a set G or something, I don't care. If you have a set G like this, and the point, for example, the point Z star here, that star here is the smallest one, so that means that star is less than all Z for any Z belong to G, and this point is have a special name. It's a is a strong minimum point. That star here is called on up the set G. Okay, so it means that if you, it means that X star is a complete solution of M and P if and only if Cx star here is a strong minimum point of Cx. Okay, strong minimum Cx star is strong minimum of point of Cx, and that is the one I write down here. Here, that is a complete optimal solution if you have like this one, but it means that X star is complete solution if and only if C of X star is strong minimum point or strong minimum element or strong minimum point of the set Cx. Okay, so it's the same way of saying strong element here. For example, this is X star. X bar here is strong minimum point of this set. And this complete optimal solution is often not applicable in practice. Not applicable in practice means that in many problems in practice there is no such kind of solution. No such kind of solution means that it's terrible. Okay, it's not the right way. It's not the right thing. So so people think of another definition for the solution. We call it Pareto optimal solution. Pareto optimal solution is a bit, the definition is quite hard. I think it's quite hard. It's really quite hard. And so you have to think of it, to practice on it at home. Is that okay? And the statement, the statement is very crazy. Upon X star in X, that means the feasible point of the linear programming, multi-objective linear programming, is said to be Pareto optimal solution. That is a very useful kind of solution. Many you can type in the internet that Pareto optimal solution, and you see that there's a lot. That is often used in practice in problem in economics or something like this. Pareto optimal solution. X star is a Pareto optimal solution of the multi-objective linear programming if very strange way, that does not exist another X. That does not exist another X. So that means does not exist X star, another X means that X different from X star, you know? There does not exist another X, such that you have this, the two conditions satisfied. The first one, ZIX less than CIX for all I. And the second, ZJX different from ZJ of X star. So what does it mean? The first condition, listen, the first condition means what? The first condition means that Cx less than or equal C of X star. You see? That does not, you remember, that does not, no assist. No assist and X different for X star, so that means, what does it mean? That means that X is better than X star, because Cx is greater than, less than. That means it's better. But the second means the second condition here for at least one j. So that means that Cx is less than or equal. Less than or equal means what? Less than equal means that C1x less than C2x. C1x star. C2x less than or equal C2x star. Something like this. C3x less than or equal C3x star. But the second condition means that at least one is strictly less than. At least one. For example, there is one. Strictly less than. Not equal. Every other is less than or equal. Another one is strictly less than. So that means there is one thing. So you can write down like this. It's strictly less than. Like this. So it is not even better, but it's strictly better. You know. That means that there is nothing which is really or strictly better than that. You know? X star is a Pareto solution of the problem if there is no one which is different from that point, but it's really better than that one. Understand? I tell you, difficult. Okay. The bonds let's put something there. Let it there. Is that okay? We study something more. You have a set A, non-empty in iron. Y bar is called a Pareto minimum of A. Pareto minimum of A if A intersect with Y bar minus Rn plus equal exactly Y bar. That is Pareto minimum of a set. Pareto minimum of a set. So it means what? Like this. You have here. You have a set A. Is that okay? Set A is something like this. A. And upon Y bar. Suppose that you have Y bar is here. Y bar is in A. Is that okay? It is called a Pareto minimum of A. If A intersect with Y bar minus Rn plus. What is the set Y bar minus Rn plus? Who can tell me? This is minus Rn plus. You see it? The red one here. The red one I make here. Hello, you see here?
Yes, sir.
Minus Rn plus. That is minus Rn plus. And Y bar minus Rn plus means that this set you translate to Y bar. Is that okay? Translate this set, the set here, translate to Y bar. So it becomes what? It becomes something like this. The blue one is Y bar minus Rn plus. Is that okay? And in this case, the intersection, the equality here is satisfied or not. You have here Y bar minus Rn plus intersect with A is the red one, intersect with A here, it's just only 1 point, y bar. Is that okay? You understand?
Yes, sir.
This set y bar here, the point y bar here is called the Pareto minimum of A. So can you tell me where are all the Pareto points, minimum points of this set A? Somebody can tell me. Come from what? I make some name for you to easy to do. This is A. This point is B. This point is C. This point is D. And some point here is E. So where are all the Pareto minimum of A? AB, all the point in AB, BC, CD, DE, or EA? The set of all Pareto minimum points of A. Ready to write down 5 points for you. Any? Hello?
I think DC.
BC. That is okay. What's your name? Who is talking? Who is just talking? Hello?
Minh Quân.
Minh Quân. Okay, you are again Minh Quân. Okay. That's right. All the point in from B to C here. From B to C. All the point here are Pareto minimum. So I tell you, for example, the point, if you take a point, for example, small a in the segment AB, and then you see a here minus r and plus is what? It's like this. And what is the intersection? The intersection is all point from A to B here. You see, intersection, not only one point. So all the points in AB here are not Pareto. Pareto just only from B to C. Pareto point are the point in BC. Is that okay? That's Pareto point. And now we come back to the Pareto solution here. By the Pareto for solution here, X star here is a Pareto solution of the problem. Is the same as saying Cx star is the Pareto minimum point of Cx. You know, Pareto minimum point of Cx. So what does it mean? It means that you have here, for example, you have here this. This is Cx. Is that okay? Cx. And the set of all Pareto min points of Cx is what? Here, if I write down here is A, this is B, this is C, D, and E. For example, Cx is it A, B, C, D, A, E, like this. This set is Cx. So All the Pareto minimum point of Cx are what? You see, if you take a point here, is that okay? If you take a point y bar here, or z bar, if you take a point, if you take a point z bar here, then and you write down the cone z bar minus Rn plus, then it is this. And in the set with Cx is only one point z bar. Is that right? Is that right? Đăng Khoa? Hello? And so z bar
Yes, sir.
is a Pareto point of Cx. And all the Pareto point of the Cx are all point in AB. That right? Are all point on AB. You know? And if you have something like this, if you have the point the set x somewhere here, if you said the set x is here, is that okay? Set x is here, and Cx, and by the map, I say it here. This is a set x, and by the map C, the linear operator C transfer this to Cx, and the Pareto points of Cx are here, and then if you by the definition there, you see a Pareto optimal solution of X star is a Pareto optimal solution of the multi-additive linear programming if and only if Cx of Pareto point C of C of X star. X star is somewhere here, so Cx star, that is equal to C of X star somewhere. Cx star is a Pareto minimum point of Cx. So if you see that all the point here, for example, in ST, all the point in ST here by C become AB. So it means that because all the point in AB are Pareto points of Cx, so all the point in ST here are Pareto solution of the problem. You understand? So in order to find out, so you have the problem, multi-additive linear programming. Now you have an idea. You have the multi-additive linear programming. You draw the feasible set, and you take the map C. You take the image of the map C of this to Rn, to Rk, and you have the set Cx. Is that okay? And you find out all the Pareto points of the Cx, and all the point on the set X that by C become to this, then all these points are Pareto solution of the linear programming. You understand? But the key point is here. The Pareto minimum point of A defined like this, and the Pareto solution defined like this, does not exist or something like this. So I say here, it is the same as saying X star is Pareto solution of multi-additive linear programming, the same as saying that Cx star is a Pareto minimum point of the set X. Why? Why? Exercise. This is an exercise for you. Is that okay? What you have to prove is the definition like this. So y is equivalent to this. See? Okay, that is your task that you work at home. Another thing is we call a weak Pareto. There is something upon y bar in A is called a weak Pareto minimum. Weak Pareto minimum point of A. Weak Pareto point of A. The condition you compare these two conditions. Pareto A intersect with y bar minus y and Rn plus. Is that okay? And here is A intersect with y bar minus interior of Rn plus. Interior of Rn plus is what? Minus interior of Rn plus. So what is it? Remember, minus there. You minus interior. Interior means there is no border. That's minus Rn plus is Rn plus minus Rn plus, but interior is no border. Is that okay? No border is this. And now you take y bar minus this one and intersect with A is empty. So look. Look at y bar here. Y bar is the same y bar as before. The same y bar is before here. Is that okay? And you minus interior. And it becomes this set. And because it becomes this set, but it has no no border. You know? No border. No border means here is something like this. So intersect with A, then it is empty. Is that okay? In this case, you see that A intersect with y bar minus interior of Rn plus is equal to empty. Is that okay? And so all the bond that we say it is a Pareto bond there is still weak Pareto bond. So all bonds here, all bond from B to C, all here from B to C here still weak Pareto. So it means Pareto bond also weak Pareto bond, but something is different. Look at the set AB. You look at the part AB from A to B. It is like this. Is that okay? You take upon y bar. Now we take upon y bar here. And y bar, if you y bar is here, and then if you plus minus interior, y bar minus interior of Rn plus is like this. No border, you know, no border means like this. And then you intersect with A. You have some point like this and no border, intersect with A and still empty. Is that okay? So this condition is still whole. And so y bar AB on the point in AB or point in AB here is not Pareto, but it is weak Pareto. So for all set of weak Pareto are all born from A to B, this, and from B to C. Okay, and so we have something like this. Pareto bonds imply weak Pareto bonds. Each Pareto bond is a weak Pareto bond, but some weak Pareto minimum bond is not a Pareto. For example, some bond from AB here are weak Pareto minimum, but not Pareto. And then the last, very sorry, a bit late, but I tell you about Pareto minimum solution. Where is the weak Pareto minimum? Here. We say X star is a weak, no. Where is it? So it's the same as before. That means that X star is a Pareto optimal solution if Cx is Pareto bond of the set. If it is a weak, X star is a weak Pareto optimal solution of the problem. So it means that Cx star is a weak, like this, a weak Pareto bond of the set. So Pareto bond, X star is a Pareto solution, then Cx star is Pareto bond of Cx. X star is a weak Pareto solution of the problem. Cx star is a weak Pareto bond of the. But I see that we have some definition of weak Pareto solution somewhere. It's funny. Here is a weak Pareto solution. X star is a weak Pareto optimal solution of this problem if there does not exist an X, so that you have this. The definition is here. Does not exist an X, so that you have here. That means that you have a Cx is strictly less than Cx star. No X. No such X in X satisfy this. And it's also like this weak Pareto minimum. The weak Pareto minimum of this set Cx star with, and this is also an exercise. How to transfer, how to prove these two are equivalent. Okay, exercise for you. And now it means that we already finished the very important part is the notion of solution of this problem. Is that okay? Tomorrow we continue with how can we find out the Pareto solution, complete solution, weak Pareto solution of the multi-adaptive linear programming. Try to come to the class tomorrow afternoon. Is that okay? Because this part is very important, and this chapter is the key chapter of the final exam. Is that okay? Tomorrow is Saturday afternoon, June 4th. Today is June 3, okay, June 4th. Okay. Okay, bye-bye. It's a bit late. I don't know if some of you have any other class, but yes, tomorrow I will repeat a bit here. Okay, thank you for listening to the end of the class. Bye-bye.
Goodbye, sir.
See you tomorrow. Okay, remember tomorrow to come to the class.